Hello, everyone. Good afternoon from Brussels. Good morning or good evening, depending on where you are. We have, for the time being, 54 participants from very different countries, I guess, but I'm sure that many others will join along the session today. Welcome to this webinar organized by IBTC, the International Biomass Torrefaction Council, and WBA, the World Bioenergy Association, on the valorization of agricultural residues through torrefaction. My name is Cristina Calderon, and I'm the General Manager of IBTC. I hope you can all hear me well and see the presentation all right in your screens. I believe that after these years of online businesses, we all become experts in webinars and this kind of tools. But still, before moving to the content, I would like to mention a few practical details. First and very important is that during the first part of the meeting, you remain muted, please, so we avoid any background noise and not to bother the others. And maybe to allow a better connection, I will also ask you to turn off your webcam, at least when you are not talking. If you have questions during the presentations, please write it on the chat. We will keep an eye all the time on the chat. And we will take the time for those questions right after the presentations or during the group discussions. Please make sure that you encode your first name and the last name in your participant tag, so we will be able to see who is online and also who is posting the questions on the chat. If you face any technical issue on Zoom, you can also write it on the chat. Please address it to Bioenergy Europe, to me, or to IBTC, and we will provide you the necessary support. And last point also that I wanted to mention from the beginning is that we will send all the presentations to the participants after the meeting today, and the recordings of the sessions, also the group discussions, will be posted in IBTC and WBA websites very soon. So this is the agenda of the day, where we are having first a plenary session, I call it, with a few presentations. You will see two main ones from Michael Wild, President of IBTC, on torrefaction, the technology, the benefits, and the market situation. And another one from Jaap Kiel from TNO on eliminating some of the limiting features of agricultural biomass by pre or post treatment. Afterwards, we will have 6 very short presentations from companies with experience on torrefaction and the utilization of agricultural biomasses. So there will be like very short and quick presentations. And right after these short introductory presentations, we will split the participants in 3 groups to join the group discussions that you wish. So at this point in the agenda, when we open the group discussion, you will see a pop-up message in your screen inviting you to join some of the group discussions that will be moderated by the torrefaction companies. You see that the room number 1 is related to the feedstock aspects. The room number 2 is focused on the torrefaction technology, and the room number 3 is focusing on the customer perspective and the performance of the final torrefaction material. So you are free to choose any room discussion that you wish, and actually you can also switch from one room to another in the meantime. That's all from the introductory part of the session and in terms of indications for today. So without further delay, I will give the floor to Christian Rakos, the president of WBA, to introduce his organization, but also to say a few words on the potential of agricultural biomass, opportunities, and maybe some possible challenges as well. Christian, the floor is yours.
Thank you very much, Christina. Welcome to all of you. On behalf of the World Bioenergy Association, our association has in the last couple of months organized a whole series of webinars on the use of agricultural residues as a feedstock for energy generation. We covered different aspects from the combustion technology all the way to the logistics, to different ways of compacting agricultural biomass. And torrefaction is, of course, one more technology to make this material with by its original form not very useful as a fuel into something that is useful, that can be used in different plants, in industrial plants, but also maybe in medium and small scale plants. So I think the interest in this subject is great. The International Energy Agency, in its scenario for net zero that was published a couple of weeks ago, which is really a landmark publication, has indicated that agricultural residues will play a very important part in the future of the world's energy consumption. Overall, bioenergy will contribute at least 20% to the entire energy demand in 2050, according to this scenario. So we're really looking forward to something that is set to grow, that is technically challenging, absolutely, but it's well worth dealing with this and getting a deeper understanding of what is possible and what are routes to take to make agricultural residues used in a greater amount. For the time being, this is not the case. Most of the agricultural residues are either left in the fields to rot, they're put back to the ground, or even burned in the fields. And this really needs to change. And I'm very glad that the World Bioenergy Association can organize this webinar together with the International Biomass Torrefaction Council. I wish to all of you an interesting afternoon, and I'm going to hand over now to my friend Michael Wild, the president of the IBTC. Michael, the floor is yours, please.
Christian, thank you. And I can only pick up what you have said. It's very great that we can organize this webinar together with WBA as IPTC. The International Biomass Torrefaction Council is looking for long into agricultural biomasses, or I have to say its members are looking for long into agricultural biomasses. It's sometimes a bit difficult to define what is agricultural biomass and what is non-agricultural biomass. We draw the line mostly in woody and non-woody biomass, because the non-woody biomass basically is agricultural biomass. And if we speak about fast-growing species like elephant grass or something like this, so we still consider this also in the overall frame of agricultural biomass, so non-woody biomasses as such. Briefly to the International Biomass Torrefaction Council, could you swap the next slide, Christina, please? The IPTC, International Biomass Torrefaction Council, is established within Bioenergy Europe. It was established in 2012 with the idea to promote thermal treatment of biomass, the torrefaction of biomass, and torrefied biomass, torrefaction biomass products as such. We have by today 23 members, which we structure in full members, developing members, and associated members. What does it take to become a full member? It takes you to be a company for real in torrefaction, meaning you're a company that is either producing and having an installation running, producing torrefied product. You're an equipment supplier to these processing plants, or you're a consumer or consuming application supplier to the market. A developing member is a member that is on its way to become a full member, but eventually has not yet completed its plans or its activities completely. And an associated member is a member that has eventually no direct business interest or an indirect business interest in torrefaction, such as research companies, consulting companies. We are always open new members to join us. Also trading companies, if wanted, can join us. Aside of the general activities of IBDC, which is organizing webinars, organizing participation at trade fairs, at conferences, at symposia. One of the big benefits of such an association is also the informal interaction that can be established between the members. And I think this is an important aspect, which eventually is a bit less on the active side in times where we have only online meetings. But the times when we had personal meetings, the coffee breaks were mostly extended because this was so interesting for the members to participate and to exchange their opinions. Now, today I was asked to give a brief introduction to torrefaction as such and torrefaction of agricultural biomasses. Now, I don't know, I'm always a bit ambiguous about how deep should I go with torrefaction or where to start with torrefaction. Torrefaction is by now more than 10 years around and was introduced at so many conferences that I think most of you are very well aware about what torrefaction is. I mean, torrefaction basically is a thermal treatment of biomass. You take biomass and you treat it thermally. This starts when drying is done. So when you put dry mass into a reactor or into any other device that heats up the biomass to eventually 300 degrees or more, then you start to split the biomass, you drive out the volatile matters and you concentrate the solid matters, very much dependent on the temperature and the resident time in the reactor and also the technology applied. You achieve a mass loss of 30% combined with an energy loss of only 15%. This is when you produce or you dedicate your production towards fuel, where you try to have a lot of the mass concentrated into the solid fraction, a lot of the energy concentrated into the solid fraction, still achieving all the characteristics of a coal or a charcoal, so brittleness, water resistance. If you go higher in temperatures, you drive out more of the volatiles. The volatiles tend to pick up more of the energy from the input material, and your energy balance looks a little bit different. You concentrate the solid biomass higher in carbon, so the energy content is much higher and the calorific value is going to be higher. Would we go to the next slide, please? The carbonization curve describes what I have described now with a lower and then higher degree of devolatilization. Lower degree of devolatilization we usually call torrefaction. Torrefaction, Christina, please go to next, continuously now. Torrefaction means you drive out about 20 to 40% of the volatiles, meaning an increase in calorific value on basis of wood or of a agricultural biomass with not more than 2% ash. We will increase the calorific value up to 21, 22, 23 gigajoule gross calorific value. That seems to be a sweet spot if product is dedicated for co-firing in coal power plants, because here we have a sweet spot in efficiency for the process and for the supply chain. Going higher in temperature, very often the expression pyrolysis is used, and if we go even higher in decarbonization, meaning we increase the temperature to 600, maybe even 700 degrees C, we speak about carbonization or high temperature torrefaction. Here we drive out 80 to maybe 90% of the volatiles, meaning that the carbon content in the solid biomass then is 75% or more, and we fall already quite well also under the definition of charcoal. All these processes can be done in a single step or in multiple step processes, always said after the drying. So the drying is always the first step and then the carbonization starts. Next slide, please. Torrefaction is such, and we look here now into the energy balance, and I addressed this already briefly. Torrefaction, if you go into standard torrefaction, sweet spot is about driving out 30% of the volatiles, meaning approximately 21 gigajoule net calorific value of the final product. That provides an efficiency for the overall process. Christina, please. That provides an efficiency for the whole process of about 77%. When we look into carbonization, it is important to understand that quite a lot of the energy is lost into the gaseous phase. So not all the energy is left with the solids, but there is a lot of energy into the gases left. Now, that from an economic point of view, but also from a sustainability point of view, means something has to happen with the gas. You need to create value from the gas, either by using it thermally, meaning running all the process for drying and the carbonization with the energy in the syngases, but usually there is a surplus in syngases, which could be easiest used in the form of turning it into heat, which then could be turned into steam or any other purpose. There are other ways also to utilize the gas. The gas is a whole cocktail of chemicals and molecules, which can, with the right technology and the right approach, also be turned into value in quite valuable single elements that can be traded then as such. If we utilize all the energy in the solid and in the gaseous phase, we achieve a total system efficiency of up to 96%, so significantly more than if you look into torrefaction only. Just for you now to see what this is in relation to the quite traditional and common whitewood pellet process. So a whitewood pellet process has an overall efficiency of about 78%, meaning this is very identical to the torrefaction process as such. But if we go higher in temperature to high temperature carbonization or torrefaction, we will see a system efficiency which is significantly higher, however, always on the requirement to have an additional use for the gas and the additional value created for the gas. Next slide, please. How does a plant look like usually that torrefies biomass? Basically, the process always starts with driving out the water. So we have always a dryer. The dryer is very much designed for the individual feedstock, be it wood, be it an agricultural biomass, be it a belt, be it a drum dryer, whatsoever. From the dryer itself, then the next step or the next steps are the high temperature application in maybe a drum reactor that could be, as said, in one step or in the second step. After the thermal treatment, there is a cooling, so the biomass need to be cooled down, will be milled, and will be compressed into either briquettes or pellets. What kind of reactors are common today? We see that there is a big variety of different reactors. None of them can claim to be the best reactor for torrefaction or for high temperature torrefaction. There is always a trade-off between what feedstock need to be treated to what product. And only under this framework you can define which one would be the best of the different reactors for you. We see that we have drum dryers or calciners which are operated at high temperatures, sometimes with even microwave supplement. We have Auger or screw type reactors, vibrating belt reactors, multiple Hertz reactors or dryers. We have also pressurized or non-pressurized moving bed reactors were quite common in this type. As said, there are different integration approaches. There are also batch processes which are not described here. The reactors here are always seen in continuous processes. For very high carbonization, we see on the other side also certain batch processes finding their way to market and being quite successful. Next slide, please. big advantage, or one of the biggest advantages of the thermal treatment process integration into the biomass processing is that through thermal treatment, you homogenize biomass somehow. And the agricultural biomass has more problems than woody biomass from being not very homogeneous, so being very heterogeneous. Thermal treatment homogenizes not only by drying, but also then by eliminating some of the volatiles and some of the salts which are not so welcome in the biomass as such. Chlorine, for instance, organically bound chlorine will be evaporated to a very, very large extent, being one of the major bottlenecks or shortcomings of straws or other biomasses with high chlorine content. We also see that the thermal treatment will allow an increase in carbon content to a level where the thermally treated biomass, the torrefied biomass, will be applicable in processes like in the steel making or the steel industry. We will hear in the next presentation about post and pre-treatment to eliminate some of the still unwanted elements, mostly ash components, potassium, alkali, and so on. But torrefaction definitely does open up for agricultural biomass a door to the energy, but not only energy, but also biocarbon markets of the world. And we are pretty sure that these underutilized biomasses will take a more and more important position in the overall biomass contribution to a more sustainable development of our economies. Next slide, please. We see today that the biocarbons, be it lower or higher carbonized, are traded either in form of pellets, the standard pellets like in the whitewood industry, whitewood pellet industry 6 to 12 millimeters, as agglomerated pellets, which is mostly then in the biochar or in the processing industry. Interesting because here we don't have a very high bulk density, or in a briquetted form, be it piston briquetters or be it roller briquetters in different sizes. Torrefied biomass needs to be densified for cost reasons, but also for safe and healthy reasons. If not densified, they might not be transported on bulk vessels. Next slide, please. We see that the starting point for all of us to address the coal power plants, to substitute coal and contribute to the role that whitewood pellets have been already played in substituting coal in coal power plants, is still our volume product, but it is less and less important. More and more niche products, more and more other sectors in the industry are starting to demand torrefied biomass, carbonized biomass for their processes. There are certain niches like biochar or in fertilizer. There are today still niches like homogenized biomass feedstock for gasification, a field that for sure will grow quite rapidly. But we see also the heat sector, so fuel for district heating applications, small CHPs, industrial heat processes, steam processes demanding torrefied biomass. We see the metallurgical industry running not only tests, but already quite substantial campaigns on torrefied biomass. But there are also new markets coming up where the biocarbon will be used as a substitute or an additive to the plastics to make the plastics more UV resistant. we expect in the next years significant shifts from the original focus being purely energy to a more variable field of markets and applications for carbonized biomass. So not only energy, but a lot of process means or process applications as well. Next step, please, Christina. Torrefied biomass is integrated into ISO 17225 solid biofuels family. So it is, as seen here, very much focused in the standardization on fuels. However, this to date technical specification is currently under upgrading into a full standard. And in this process, there will be an opening and more flexibility towards other sectors as well. So not only as a fuel, so there will be, and this is to be seen and discussed in the next 2 years, there will be additional classes that will focus on other industries, not only the coal power plants. Next slide, please. Before I come to a conclusion, one more important step or one more important aspect on torrefied biomass. We see that we have for all of our biomasses which are transported and consumed at the site of last consumption, we have to prove how much energy and how much has been used and how much emissions have been caused in the whole supply chain. Now we have here compared the emissions cost and the energy used in the supply chain. Here we have the blue lines in this cobweb comparison, which is the reference whitewood pellets, 100%, and the orange line just does show how much energy in each of the links of the supply chain is consumed by torrefied pellets in the chain. You see that in average about 20% less energy is consumed, meaning 20% less emissions are caused, which is giving added value to torrefied product for the final consumer, because the final consumer's value of a product of torrefied biomass is closely connected also to how much CO2 substitution when substituting coal by torrefied biomass they can record and they can prove. If we go to the right side of this slide, then we compare here whitewood pellets to carbonized biomass, meaning to high temperature torrefaction application, where we achieve something like 30 gigajoule per metric ton, for instance. Here we see that we have about 40% reduction in the CO2 emissions or in the emissions and the energy consumption along the chain. So you see in logistics, there is a large savings opportunity when using torrefied and carbonized biomass, let alone that these products can be handled in the open, can be handled in the rain. So there is a lot of additional savings in investments in harbor infrastructure or at the consumer's side. Next slide, please. And this is already my concluding slide. Just wanted to repeat here quickly. The thermal treatment really does open for the agricultural biomass the door into the international biomass value chains, be it for energy or other processes where we can substitute conventional carbon. The processes that need to be applied will be mostly single step, but can be also multiple step processes, very much depending on what is needed to connect the feedstock basis with a certain product quality that is required by the consumers. And this also provides the aspect that if we split the process, so if we have value created from the gaseous phase on the site of origin of the biomass, we create there also infrastructure. We do not export all of the biomasses to the consuming countries, but also in the rural areas where usually the biomass is available, we have a potential that this value chain leaves value and helps to create infrastructure. The reduced sustainability concerns for agricultural biomass and byproducts in respect to forestry biomass will help the overall sector also to keep its very positive image and contribute significantly to the overall energy balance of the global economy in the future. So for feedstock owners, so for those who have a lot of biomass, agricultural biomass at hand and don't know what to do with it, I think it's really high in time to get in touch with process technology owners. Those who will be in the panel debate and presenting their technology would be one of the opportunities. And if you have more questions to them and you would like to discuss deeper with them, please participate in these breakout Q&A sessions. We designed this dedicatedly to have smaller groups and allow a more open and more personal discussion with this. Thank you for your attention. By this, I'm ending my presentation. We'll be very happy if you address the IPTC with any questions you have here to us. The address is given on the next slide if you don't know this already. And yeah, by this, I would like to return the microphone to Christina, just to pass on to Jaap then. Thank you very much.
Thank you, Michael. Before going to Jaap, and because we are 4 minutes ahead of the schedule, we have one question that you partly addressed already in your presentation, but maybe to clarify again. One of the participants is asking, what is the main difference between carbonization and torrefaction in terms of energy content and energy input? Do you want to?
Yes, yeah, I mean, you can go back up. I think it was slide number 4. Basically, the energy content, I mean, you can always concentrate the energy which you have in the feedstock. But if we have a feedstock that on dry basis usually has an energy content, further up, please, further up, Christina. To the carbonization, yeah, to the carbonization graph. If you have an energy content of about 18 to 18.5 gigajoule per metric ton dry on a certain biomass, then just to the carbonization curve, Christina, please, 2 slides up.
Yes, sorry, before.
Then you would concentrate in a typical low temperature torrefaction process, which is around 250 degrees C. You would concentrate this to a net calorific value of approximately 21.5 gigajoule per metric ton. Be aware this curve is in gross calorific values, so therefore it differentiates about a couple of percent from the numbers I'm saying now. So in torrefaction, you would typically achieve a gross calorific value around 23 gigajoule, meaning net calorific around 21.5. While in the carbonization, you concentrate the carbon contents in the material further. So you might go up to 33 gigajoule per metric ton. Gross, meaning about 30 to 31 gigajoule per metric ton net. The energy consumption, or as such, in torrefaction, the gases which are evaporated usually are used to fuel the process itself and to substitute energy that is needed for the drying of the feedstock. Therefore, the process is self-sufficient. There is no excess energy available. In a higher temperature torrefaction, you drive out so much energy with the volatiles that you have a surplus in energy. And this was then on the next slide, where you see about 44% of the energy input in the process is available in in the gaseous phase, and this energy can be used again for the process itself, for drying of the biomass if need be. But depending on the moisture content of the feedstock that is arriving, still about 25 to 30% or eventually even more will be available to drive other processes and create value from these other processes. I hope that was a clear and sufficient explanation. Otherwise, we can happily discuss later in the Q&A.
Yes, very detailed. Thank you very much, Michael. So with this, we move forward to the next speaker, Jeb Keel. He's the Program Manager of Biomass at TNO Energy Transition. Jeb, you will share your screen, right? So
yes,
I will stop sharing mine. And now usually you will be able to share your screen.
Yes, do you see my screen?
Yes, perfect.
The first slide?
Yes.
Yes, so after this very nice introduction of Michael Wield to torrefaction, I will be happy to shed some lights on the potential of torrefaction for agricultural biomass. So I think the general message of my presentation will be that torrefaction is not a panacea. It is not the solution for every issue when it comes to agricultural residues. However, there is a clear potential of torrefaction, especially if you combine it with washing. So to clarify this conclusion, I will go in my presentation, start first with from the general issue that woody biomass is under debate. That agricultural residues are largely unutilized and really are there in very large quantities. Then dive into the properties of these agricultural residues versus clean wood. Look at, well, what about torrefaction as a solution? And then illustrate that with an experimental assessment we did quite detailed at TNO, including economics, and then come to some summary conclusions. So first, of course, you all know woody biomass is quite under debate. I think you all know examples of that. And that has led, for instance, when you look at the EU Fit for 55 package, so to meet our EU targets in 2030, it has led to a reinforcement of the criteria for forestry biomass, forestry-based biomass and bioenergy. So it will be prohibited to source biomass for energy production from primary forests. No support for forestry biomass in electricity-only installations as of 2026. A prohibition of national financial incentives for use of logs, stumps, and roots for energy generation. All biomass-based heat and power installations should comply with minimum greenhouse gas savings thresholds. And this will also apply for relatively small installations. So there is increasing pressure on woody biomass. But then if you look at the potential of different biomass sources, let me go back. Then you see that you see here an overview actually of different studies, a figure that was published in the Bioenergy Europe Statistical Report of 2020. And you see in orange the enormous potential of agricultural biomass, if you compare it to, for instance, the forestry biomass, which is in green. And this has been compiled by my colleague André Fay. So you see there is really an enormous potential, and you also see when you look at the numbers for 2018 that this potential is hardly utilized at the moment. So there is may expect an enormous growth of the use of these agricultural residues. However, that is not straightforward. Because when we look at the properties of agricultural biomass, you can say it's a quite difficult feedstock. Well, what is this? It is if you compare it with woody biomass, generally it has lower density, inferior transport, handling, and storage properties. For instance, if you think of straw and empty fruit bunches.
We see a pop-up window for the breakout rooms, or it's only me. Sorry, it's only on my side. Sorry.
Okay. I see some things popping up now and then, but anyway. As I said, lower density, difficult storage, handling, and transport properties. In general, a higher moisture content, and that poses a severe energy penalty when you have to evaporate that moisture. In general, the organics content is higher, and these organics are also more problematic. For instance, when you look at chlorine, alkali metals, sulfur, heavy metals, which may lead to pollutant emissions, slagging, fouling, corrosion, catalyst poisoning. So a lot of difficulties also in the process itself, and also a negative impact on it may have on ash utilization. Well, what about torrefaction? Well, in general, you may say that torrefaction does a great job in increasing the density, energy density, and improving transport, handling, and storage properties, also for this agricultural biomass. However, if the biomass is very wet, and you could say, well, let's say above 50% moisture content, then perhaps it's better to go to wet processing, like digestion, fermentation, or hydrothermal processing, and not rely on torrefaction. And also, it is the case that torrefaction has limited potential to mitigate the problems of these problematic inorganics. It does little to decrease their concentrations in the product. However, if you combine torrefaction with washing as an additional unit operation, that may be the way forward. And so if we look at that, torrefaction and washing, then first of all, I think it's important to make the statement that it's essential to optimize the overall process layout. So that means minimum freshwater consumption is essential. So washing water recycling should be included, preferably countercurrent washing to make it more effective. Dewatering after washing should be paid a lot of attention to. And clearly, we should pay proper attention to the washing effluent. I will go into detail concerning this somewhat more later on. Well, you could, of course, do two things. You could do torrefaction and pre-washing, so first wash and then do torrefaction. That leads to a quite good solubility of these inorganics and thus higher removal efficiencies. But the dewatering will be rather difficult because the material is not hydrophobic yet, which it becomes upon torrefaction. And so that also means energy consuming. And in general, this is a preferable route for relatively wet biomass. But still relatively wet below the 50%. You could also do torrefaction and then afterwards wash the material. That leads to lower removal efficiencies, although they might be only slightly lower depending on the feedstock. It leads to easier dewatering due to the hydrophobic nature after torrefaction. It also leads to lower organic loads in the effluent, which makes effluent treatment easier. And this may be preferable for relatively dry biomass. Well, I would like to illustrate this and dive into more detail on this by showing some results of a quite detailed study we did on this combination of torrefaction and washing. And in this study, we looked at various types of agricultural residue. And I would like to acknowledge my colleague Pedro Abella, who did a lot of the work in this study. So in terms of experimental approach, we did experiments at 3 different scales. So from lab scale to bench scale to pilot scale, and always combined torrefaction and washing, both pre-wash and post-wash we did. Well, first of all, if you do this and you look at the mass and energy yield and the heating value of the material, basically you see similar things as for torrefaction or woody biomass. You see an increase of the heating value. You see relatively limited mass loss and a high energy yield. And of course, it depends on the combination and the conditions, how the numbers will be exactly, as Michael already showed. And you see that in washing, you also lose mass. And of course, that's also what you want, if provided it's the proper constituents of the biomass you lose there. Well, to get some idea of what is the effect of this combination on the inorganics, then basically you see 2 examples here for miscanthus and for roadside grass. And in general, we can say that torrefaction has limited effect on chlorine. The organic chlorine it may remove, but the inorganic chlorine, for instance, in the form of potassium chlorine, will in general not be removed by torrefaction. And so torrefaction also has a little effect on potassium. However, if we combine the 2, then from these graphs, you can see that, well, it leads to an excellent removal of the chlorine, also the inorganic chlorine, also for the potassium and the sulfur, and well, the sulfur and the potassium, and the sulfur and the phosphor to a more limited extent. But especially the potassium is very essential when you look at, for instance, slagging and fouling propensity of the material. Now, to look at, well, what does this mean in terms of thermochemical conversion? We did some combustion tests in a small combustion simulator where we can mimic pulverized fuel combustion conditions very well. We use that in that installation a lot, and we know let's say, how it compares to large scale operation. And we did various tests in this installation. And well, here you see one of the results. Here you see where we looked at particulate emissions for roadside grass. Left the roadside grass itself, and to the right upgraded roadside grass, so in this case pre-washed and then torrefied. And in general, you see there that the share of submicron particles, so very fine emissions, becomes much less after upgrading. And you also see in the table the results for some other feedstocks. So in general, you see a quite substantial reduction of submicron particles after upgrading. And this is something that in general with agricultural biomass is quite an issue. It is also an issue that will become more important in the near future. And you see here the clear prospects of torrefaction plus washing to do something about that. And well, that also has a clear impact on the fouling propensity. So we did some tests where we had a fouling probe, so simulating a boiler tube, and looked at the degree of fouling depending on whether you have the pure biomass or the upgraded biomass. And you see here in the graphs that actually the fouling propensity decreases significantly when you do the upgrading. So much less fouling issues after upgrading. Well, then we moved also towards, let's say, looking at the economics. And for that, of course, first you have to translate these experimental results into a industrial process. And that's what we did. We looked at, let's say, such a process at different scales. And here you see an example where we looked at a process for roadside grass, 120 kilotons per annum dry biomass input. And we designed the process as such. So first a washing step, then a mechanical dewatering, a thermal dryer, a torrefier, and a pelletizer. And connected to the washing step, there was a digester, an anaerobic digester, as well as a dedicated water treatment plant. And this all is needed to treat the effluent in a proper way. We not only looked at roadside grass as such, but also we looked at silage storage. So to first do the silaging process, and then looked at the behavior of roadside grass in such a plant as well. And this to overcome seasonality. Of course, roadside grass is only harvested during part of the year, and if you want to operate such a plant whole year round, then this might be an option. Well, we did detailed mass and energy balances for such a plant, and on the basis of that, we did the economics. And here you see one of the results, and more details you may find in the publication, for which the references are indicated. And basically, we found that for a case in the Netherlands, and of course, all these results are very case specific, but for this case, where we assumed, let's say, plant size of 100 to 150 kilotons per annum, and a negative gate fee of 25 euros per ton, that led to a quite attractive IRR of 15.6%. Assuming a price for the biocoal produced of 80 euros per ton, which is, it could be quite attractive compared to both wood pellets and coal prices. So here you can see that there is quite a reasonable business case, despite all the measures you have to take with the washing, as well as the cleaning of the washing effluent. Despite all that, you still can have attractive business cases. So in summary, I would say agricultural biomass, there is a huge potential. It's largely unutilized, and there is a large potential there, but the properties are in general more difficult than woody biomass. Torrefaction as such is not a panacea, but a combination with washing may help out, has clear potential. It's essential to optimize the overall process layout, as I indicated. And in general, you could say that the pre-wash is preferable for relatively wet biomass and a post-wash for relatively dry biomass. And attractive business cases appear feasible, but of course, they are largely dependent on local conditions. And with that, I thank you for listening, and I will be happy to answer any questions via the chat or later in the chat room, in the breakout room.
Thank you, Jaap, for this. Quite interesting to see. And yeah, as you, I can only repeat. I mean, there is no jack of all trades, not a single technology that can achieve all and everything at once. It's always the combination, and therefore it is always important to know precisely what kind of feedstock you're aiming to process, and on this basis, then the right pathway for the processing can be selected, so that you can successfully offer then your products on the market. by this, and I mean, I'm pretty sure there were plenty of questions now coming up in the minds of the audience on this, at least for me, during seeing your graphs. And so I'm sure I want to continue this discussion, but please keep your questions for the Q&A sessions, which will start in about half an hour, and join then the one with Jaap on the panel there to discuss this. And please don't forget, you need not to decide and you're stuck forever in this one Q&A session. You can also choose and wander around between the Q&A sessions. We try to mimicry a live meeting or a personal meeting as close as possible by this. But now I would like to start our panel session, a panel session intended to give you a couple of companies that have a successful story to tell about implementing their technology on all kind of biomasses, including agricultural biomass. So therefore, please let me start with introducing Perpetual Next, a company that has taken up the technology of CEG, and is recently one of the first companies starting to run industrial scale plants. But this will be all explained to us by Bart de Vries, the product manager of Perpetual Next. Bart, the floor is yours for about 5 minutes.
Yeah, thanks, Michael, for the introduction. So indeed, my name is Bart de Vries. I'm product manager at Perpetual Next. So maybe I can give a bit of background of the organizational setup. So here you can see Perpetual Next consists of 3 divisions: trading and commodities, conversions, and technologies. And we have different assets in both in the UK as in the Netherlands. But if you can see on the right side, there is the Baltania conversion side, which is the commercial plant where we started this month full production of torrefied materials. We will do their palletized and bulk shipments from Baltania. And we have a contract signed with ArcelorMittal to provide perpetual carbon biocoal to a site in Belgium. CEG is the technology company, as also explained by Michael, which is the company, and we have a site in the UK in Derby, where we have an R&D site. So also there we have 2 torrefaction lines that are we're investigating different types of feedstock as well as different applications of the torrefied material. And in the next slide, there is some more information about our feedstock program. So we looked with a number of partners to different opportunities from a feedstock point of view. We listed the 25 most interesting feedstocks and then looked at those feedstocks with a different bias. So we kind of, it is a kind of a challenge to come up with what is the most interesting feedstock. Well, you cannot say that. That depends on the bias. So that depends on the way you look at that type of feedstock. But obviously, we are looking at the feedstock on availability, on cost price, as well as the if it matches our torrefaction technology process, as well as obviously the whole the performance of the torrefied material in the application, specifically when we look to biochar options. So at the right, you can see even from different biases, different types of feedstock are now listed as our most interesting feedstocks, and we will continue to do not only the lab scale tests, but also do trials out of Derby with those feedstocks. And then the next slide. So this is to give you an overview. We also will be present in, so it will be really good to meet you face to face if obviously that's allowed by restrictions. If they are still lifted, we will be in Bremen in October, the 20th and the 21st of October at the Carbon Capture Expo, and we will have a stand there in Hall 5. But basically, yeah, this is the business that we are in. So we have the agri residues, the waste woods, all the types of feedstock on the left hand. We have our high temperature torrefaction technology, and then with that we have torrefied chips, which we call perpetual carbon, and this can become a high grade carbon solution, which we are in the end aiming for, which have all the properties that is required from an agricultural point of view. So meeting EBC guidelines, as well as having excellent properties in surface area, as well as porosity of the biochar. I think that's 5 minutes, probably that's gone. Thank you for your time.
Thank you very much for staying so precisely in time, Bart, and for this introduction, interesting introduction. I think that also will cause a lot of questions then during the Q&A session. But let me now please pass on the word to Javier Gil Barno from CENER in Spain. For me personally, Javier was the first person I've ever witnessed of entering into long-term trials of straw torrefaction. And so I think his short introduction is going to be quite interesting. Javier, the floor is yours.
Thank you so much, Michael. Yes, true. I think so. We started to focus on torrefaction. The first lab test take place in 2007 or something like that. Okay, and the pilot test already in 2009. Okay, I will present you. We are okay. Next, please. Okay, we have been working, as already mentioned, more than 10 years in torrefaction projects related with agricultural biomass. And at pilot scale, pilot scale was able even to reach up to 350 kilograms per hour production rate with a straw. Okay, and we already some years ago we were able to produce high quality straw pellets with high durability, 97%, and high book density over 1700. Okay. We have two pilot plants. One pilot plant for torrefaction with this 150 to 350 kilograms per hour capacity, depending on the feedstock and the product characteristics you want to get at the end. And also a pelletization unit, a 30 kilowatt green dye pelletizer, in which we have a lot of experience with a lot of different biomasses and different products, and huge experience in order to scale the pelletization process of torrefied biomass. Next, please. Now we are focused on developing a technology that is want to produce reliable and competitive biofuels from residual agricultural biomass. Okay, mainly focus on the next market demand, and this focus in our vision in industrial sectors with intensive thermal energy consumption. Okay, the technology combines torrefaction with other processes to eliminate certain unwanted inorganic elements, as already Jack Kiel has mentioned in his presentation. Okay, and when needed, depending of the process of the end use, could be needed to use additives also to improve the high temperature behavior of the mineral fraction. At the end, you get a solid biofuels with high calorific value, very high energy density, low emissions, and highest melting temperature. Next, please. We have already reached pilot scale, proof of concept pilot scale. We have produced up to 2 tons of product in different batches with 67% potassium content reduction, more than 95% chlorine reduction, and 57 in the case of sulfur. All the tests were carried out with the straw. And we have carried out the industrial techno-economical assessment in a production capacity in the range of from 58,000 to 116 tons per year, and we got a production cost in the range from 27 to 32 euro per megawatt hour. Next, please. Thank you so much. I'm available for any question about this development.
Xavier, just one quick immediate question. Could you just let us know what is your offer as Senior now to the market? You described your research and development. What is the offer to the audience?
Okay, due to the limited number of slides and the time, I couldn't explain. Okay, next steps for us is to carry out long-term tests to produce up to 10 tons of product, and to start testing with end users of this product. So next step for us before licensing technology in the future is to validate the product performance with end user and validate the process performance in longer tests at pilot scale.
Thank you very much for this explanation.
You're welcome.
Yeah, so addressed to all. I mean, Javier will also be available then in the Q&A session. Just choose his part to address him directly. And by this, we are moving on to another technology company, Yilkins, a Dutch company represented here by Joris Spaan. Joris, the floor is yours. Please introduce your technology and company to us and what your offer is.
Yes, good afternoon. My name is Joris Spaan. I'm business development responsible from Yilkins. I'll give you a short introduction of Yilkins as being a technology provider, what we can do for you in the business of agricultural residues. Next, please. Yilkins does have knowledge in also the treatment of biomass, already mentioned by both Jaap Kiel and also Michael, that it is very important to do this correctly, to make the good steps towards torrefaction, to get an ideal product. What we do have is in our scope is drying. So we do have an efficient drying technology, so we can build an integrated solution, drying including torrefaction. We know the route towards pyrolysis as well, to make a higher value product with a higher energy content. We combined our solutions with an own combustion, also fossil fuel free solution, and at our demonstration plant in the Netherlands we can show both drying and torrefaction, including the pelleting step, so we can make also samples for clients. Of course, it is very important to do it very energy efficient, because it's all about energy and using less energy than we do today. So that's also how we engineered our drying and also torrefaction process. Very simple and easy. Next slide, please. This is the core of our technology. It's the swirling fluidized bed technology. Mechanically, it's a static reactor, so there are no moving parts. It's small footprint, compact design, safe and flexible design. Safe also in the form of safe because we don't use oxygen in the fluidized bed reactor itself. So and that's of course taking away the chances on fire and explosions. Very fast heat transfer, so short residence times in the reactor itself, and not that unimportant. It's a TRL level 8, so the system is complete, qualified. We have a bankable solution. Due diligence is done by DNVGL. And also what we can do, we have some guarantee support on performances that we perform. Next, please. a little bit of our experiences with some herbaceous biomasses. You saw on the left side, you have seen them before, the wheat straw. In the mid side, miscanthus, banana arundo grass, all different kinds of grasses. And on the right side, Jaap Kiel told you a little bit about it. It's the roadside grass that we also did torrefaction on and produced in perfect industrial pellet within specifications. Next slide, please. A little bit more on insights on some agricultural residues. It's coca shells, olive seeds, arroyo and palm kernels on the left side, and in the middle, brewery spent grains. We work on that as well for big brewery to make that also CO2 neutral using their own residues. And on the right side, of course, the residue of sugar making, it's the bagasse. Very much potential on that agricultural material as well. Did trials on it, made a pellet of, and also tested by an energy company with a good crushability, very good step made there. So just to give you a short introduction, as I mentioned, we do have our demonstration plant in the Netherlands. On the top picture, you do see the swirling fluid as bed reactor in the middle, a little bit difficult to find, but it is there. And we do have the pellet press available as well, and the hammer mill to perform all kinds of samples for customers on demand. Next one, Christina. Thank you all for listening, and hope to see you and hear you in the breakout room later. Thanks.
Thank you, Joris, for this quite quick introduction of your technology. One of the technologies, and that is interesting, and I like to highlight this here. I mean, on all of what we have heard till now, and also what we will be hearing in the next presentations, is also just proving that torrefaction really has made it from the development scale to the industrial scale. We have TR8 levels. We have industrial plants which have started operation, which are in construction. And I think this is also one of the messages that need to be taken home. Torrefaction is an industrial technology that is proven and that can be implemented now on almost any scale wanted. By this, I would like to pass the word to Viktor Radic. Viktor Radic is representing Polytechnic, and Polytechnic has a very unique technology. I think Viktor is going to share this aside of a general introduction of the company with us, focusing on the highest purity of carbon and quite high concentration of carbon in their product. Viktor, the floor is yours.
Thank you, Michael. Good morning, good afternoon to everyone. Polytechnic is an Austrian company, a family-owned business, and mostly known for its expertise on biomass combustion. However, we've decided to enter this upcoming and new niche market about 20 years ago. And the result of our research, of our R&D of 15 plus years, is a technology called green carbon. And we have a fully operational commercial plant in Germany, which started operation in 2015. We have focused on carbonization instead of torrefaction. So going back to Michael's presentation, we focused on temperatures on the higher temperature scales, so between 500 and 650 degrees Celsius. Our system is a high temperature slow pyrolysis process. It is an automatic retort system. So what we have done is we have decided to focus on quality, so to produce an end product with high carbon content instead of on volume and quantity, which is the specialty, we would say, for torrefaction. So we have decided to build or to produce a high quality product, not for the energy market, so not as to produce fuel products or fossil fuel replacement, but to enter other markets which require vegetable carbon or biocoal, if you want to call it biochar or charcoal. So products such as, markets such as agriculture, farming, pharmaceuticals, the steel industry, and mostly focusing on carbon sequestration. Our experience with biomass is very vast. We use this facility to also test different feedstocks. As many of the speakers before have said, there is not one perfect solution for all cases and instances. The same thing is with this plant. So for a specific application, for a specific feedstock or a specific final product, it could be the right solution. We have a plant, so this one in Germany is running at 3,000 tons of output per annum. We can scale it up to 12,000 tons per year. We produce high carbon content, carbonized biomass, carbonized product. So we can reach between 80 and 95% C-fix. Very stable product. We have experience with agricultural biomass. Next slide, please. We have done different sorts of, Christina, next slide, please. Thank you. We have done different sorts of biomass residues, from corn cobs to wheat straw, corn stalks, miscanthus, different grasses, herbaceous biomass. Every one of them can be carbonized. It all depends on what the final product needs to be and how efficient the process is. What we have found out is that mostly the one disadvantage of this process, so high temperature carbonization with biomass agricultural residues, is the volume or the output. Because of the lower bulk density of agricultural residues, we can expect higher handling costs at the feedstock side and also at the final product side. So the bulk density reduces the conversion ratio. So if you're looking to produce a product, if you want high volumes, high outputs, then we believe carbonization is not the solution for agricultural residues, but rather maybe a continuous process like torrefaction. However, if you're looking for high carbon content, carbonized agricultural residues that you need to use for non-energy use, then it could be a solution for you. So we'd be happy to discuss it and test any feedstock you might have in mind. Next slide. So like I said, our main products are not, or our niche markets are not the energy market, although charcoal might be considered as some sort of a fuel. It's a small segment of the output that the plant produces. We do terra preta, animal feed, or additives, and these are just some of the applications of woody and non-woody biomass that are possible and out there. So that's about it. If you have any questions, you can contact me through IBTC, and I'll be happy to answer questions. Also in the breakout room, I think I'm in the feedstock breakout room. That's it. Thank you very much.
Thank you, Victor. And quite modestly, you have not mentioned that Polytechnic is one of the largest suppliers of boilers and is also specialized in turning all kind of agricultural biomass through normal combustion into usable heat and product. By this, we are making a big step geographically. We have James Menel with us from National Carbon in the United States, being in this board now the only representative from outside Europe. However, please let me confirm that the IPTC has more members than only one from outside Europe. So Torrefaction is not only a European initiative, but you see this globally. You see a lot of companies and initiatives in North America, in South America, in Asia, even in Australia and New Zealand, but still leading a little bit is Europe. But we'll see now from James, we learn how advanced his installations are, and that National Carbon is one of the largest installations in high carbonization torrefaction processes currently active. James, the floor is yours.
Hi, good afternoon. James Manel, CEO of National Carbon Technologies. And Christina, could you go to the first slide, please? National Carbon Technologies, or NCT, is an environmental technology company based in the United States. And we develop and produce advanced biocarbon products from a range of sustainably sourced biomass. And our products are engineered for use in a range of different global markets, including energy production, metals production, agriculture, and importantly, water purification. Today, we operate the largest advanced biocarbon production facility in North America and have been supplying customers commercially on a global basis since 2012. We hold the largest intellectual property portfolio around biocarbons in the world today, with over 200 patents that I think reflects both our innovation and it protects our process and our product technologies. And our technology was specifically designed for beneficial conversion of agricultural co-products into biocarbon. And to that end, we're actively building today over 500,000 tons per year of new production capacity that will be online in 2023 that will use primarily agricultural residues as the feedstock. Next slide, please. Our technologies were developed by a unique group of thought leaders from the biotech space, including really top engineering and science leaders from the largest biofuel and bioproduct companies in the world, including Cargill and Poet, and experts from some of the leading research universities, including Stanford and MIT. And our focus has been on the high temperature pyrolysis side. We use state-of-the-art process controls and really try to manage the reactions inside a reactor to drive different performance. And one of the advantages of going to higher temperatures in the 550 to 700 C range is that we're able to completely break down the biomass into carbon, which allows us to use a very broad range of feedstock and reduce it into a very consistent and homogeneous carbon product, regardless of the type of feedstock that we're using. To deal with some of the unique attributes of agricultural residues and co-products, we use mechanical separation on the front end of our process, and we use a proprietary catalytic elemental reduction technologies that really only work at higher temperatures to help target and reduce some of the unwanted characteristics, including alkaline salts and including some of the metals that are inherent to a range of different agricultural feedstocks. Our process ultimately results in high fixed carbon, low ash products, and again, are engineered to be drop-in replacements for fossil-based products like coals, like high-grade coals like anthracite and cokes as well. And also, because we operate at high temperature, we have an abundant amount of self-generated biogas, as Michael had articulated in his presentation, that allows us to both reduce production costs and have a very low life cycle environmental footprint with self-generated bioenergy. Next slide, please, Christina. So we've patented the use and actually demonstrated at commercial scale use of more than 50 different types of agricultural residues and energy crops, including everything from nutshells to miscanthus. And we're able to tailor the products to meet the different specifications that are important for end users, whether it's fixed carbon, whether it's very specific ash content or compositions, grindability for power applications or PCI applications. And we've demonstrated the ability to meet customer specifications in these market segments using a range of agricultural feedstocks. And importantly, we've done it in very demanding market segments like drinking water purification, where we supplied more than 50 cities on a global basis and purified the drinking water for millions of people while using agricultural residues as a feedstock source. Ultimately, we're tailoring high-performing biocarbon products using a range of feedstocks, something we've been doing for a decade, something we like doing. We're always excited to keep advancing this work with new feedstocks and new partners. Thank you.
Thank you very much, James. I mean, that was quite comprehensive and quickly run through a quite large portfolio, and I'm pretty sure there will be quite a number of people which will come with questions to you in your Q&A session. By this, I would like to pass on the word to our next and in this webinar last panelist, Wolfgang Moser of Next Fuel, Austrian-Swedish company. Wolfgang, floor is yours.
Thank you, Michael. Thank you. My name is Wolfgang Moser from Next Fuel. Our company was founded around 2010, and we are a technology provider. We operate a pilot factory in Austria with an output capacity of 1 ton. That's one of the pictures that you can see here. But our main offering is all the engineering services, testing, development services, and then the license for our technology. And that's what we offer to our project partners on a global scale. I'd like to share with you 3 main topics and 3 experiences we made with agricultural feedstock during our development and research process. And on this first slide, I'd like to focus on the chemical composition, on the ash content. I can more or less confirm everything we heard from Jaap Kiel, also from our practical testing perspective. The main 3 steps that you can see here, we take some feed material, in that case, elephant grass or banana grass or other energy crops, put it in the reactor and create the output. Okay. We have already had 3 different large-scale tests with around 10 tons output in the end, where we received grass like this with unsatisfactory ash content. And through one of our technology partners, Andritz, we put it into a pulper and could reduce exactly the amount of chemicals that were an obstacle to good product specifications in the end. The amounts of reduction can be influenced by the duration and especially by the temperature of the rinsing, because this has been one of the questions in the chat. So it's in the lab we could reduce up to 80 or 90% of the minerals if required, but it's an economic question to say how much do we need to reduce, and that's the driver for setting up the right parameters for this washing and drying process. But that's number 1, ash content, chemical composition. Yes, this can be influenced also in a large-scale production run, and that's what we have proven here. A second topic, Christina, next slide, please. You can see here the production flow through the factory, but when you look at the picture with the front loader, here is the straw, here is the feed material from one of these test runs. And one special property is usually the very low bulk density, especially when working with straw. And low bulk density can be a problem in all conveying systems when you get limited simply by the volume of available conveyors, even by the volume of the reactor. And our experience was, on the one hand, you can optimize many little things in the whole conveying system to get over this problem. But the other and more interesting experience quite recently was to apply pre-densifying. So in fact, when getting extremely light material, we found out it's also a good option to apply densification first. This can be done, for example, by standard pelletizers, and then use the densified material throughout the rest of the process. Of course, then you don't even need a densification step in the end. So if this is one of the specific hurdles, and in some cases the feed material can come really at very, very light bulk density, then pre-densification can really be a solution to it. And the third topic, when I go to the next slide, is one that we experience also in our first commercial scale project. We are in the engineering and permitting phase for a large scale implementation in Finland, and the feed material used there are forest residuals. Now with forest residuals, it's similar like with other agricultural residuals also. You get a mix of quite different things. And inhomogeneous feed material is always a challenge because you have different elements reacting to different process parameters differently. So in that case, we feel that applying some pre-processing steps, simple steps like screening, for example, sieving out fine materials to get a better and more homogeneously defined feedstock is a potential solution which drastically improves the quality of the end product. So these were my 3 topics to share with you, because I feel we've heard a lot about torrefaction process as such, but the specific challenges for residues are like this ash content, specific weight, and homogeneity of the feed material. Any more questions in the discussion rooms? So thank you for your attention.
Thank you very much for this, Wolfgang. Very interesting thoughts and contribution, and I'm pretty sure there is a number of other limiting factors for agricultural biomass, like seasonalities or other things, which we can all discuss then, I think, in the Q&A session. Thank you, all the panelists, first of all, for your very, very interesting contribution, and secondly, for keeping your timeline so precise. To the audience, we have designed now a Q&A session, which is happening in 3 different breakout rooms. Our intention when creating this structure was to allow a more intense discussion and a more direct discussion between participants, member of the audience, and our panelists, because the groups will simply be smaller. However, as said before, you may roam between the different breakout rooms, and when all your questions were addressed and discussed in the one room, please feel free to move on to the next room. We have structured the rooms now in 3 elements. The one is concerning the feedstock aspects. That will be moderated by Jaap Kiel and Viktor Radic together. The second room will have a focus on the torrefaction technology as such. That will be moderated by Bart de Vries and Joris Spahn. And the third room will focus on the consumer perspectives and the performance of the materials resulting from the different processes. Here we will have Xavier Gilles, Wolfgang Moser, and James Menel moderating this panel. However, it needs to be said, although we have structured the rooms like this, we know that there is no clear borderline, and you are not permitted to put the one question only in one room. Just wander around and see who could help you with your problem best. By this, I would hand over quickly to Christina, who shall repeat the modalities and introduce you how to best choose now and which buttons to click on your screen. Christina, please.
So very soon I will ask my colleagues at IVTC and BioEnergy Europe to send the options to you. So you will see this pop-up message with the 3 rooms. Those are the topics. So rather, if you have an interest on one specific topic, or you have a question that you want to address to any of those speakers, you can join this room. As Michael already explained, you can change from one room to another. This is an open-end webinar, so we have allocated about 20 minutes for discussion, something like this, but if the discussion is very lively, we can continue longer, so hopefully it will be like this. Do not hesitate to ask as many questions as you have, because this is an opportunity that we want to offer to the audience, especially in these times that networking is being more and more difficult. So yes, also maybe to tell you, like, do not go back to the plenary session, because the plenary session will stop here, so will be empty of content. All the questions, all the discussions will be in the 3 different rooms. And that's all on my end. So now I ask first the moderators of each of the rooms to please join the room that are assigned to you, also to the secretariat, and then the participants join the room that you wish, and I hope that you find the discussion of your interest. So thanks a lot for participating, and see you soon. Keep tuned on IVTC website on the next events that we will organize, and also to download the recording of this event. Thank you very much for your participation, and hope to see you soon.